All right, welcome back to Applied Algebra and Trigonometry. We're going to be talking today about trigonometric identities. Let's go through a basic trigonometry review. We need a right triangle and a given angle to do that. Now that we have identified an angle of interest, we can name the sides of this triangle. We have the hypotenuse, which is always opposite the right angle. We have the side adjacent to the angle. In fact, that side forms part of the angle, one side of the angle. And we have the opposite side, the side opposite the angle. And now it's time for your review of ancient Greek. And the word so, ka, toa, standing for sine, the S at least. The C stands for cosine, and the T stands for tangent. The O and the H, well, we use that to say that the sine of theta equals the opposite over the hypotenuse, also written as O over H, SOH. So the next word means the cosine of theta is the adjacent A over the hypotenuse H. And finally, we come to the tangent. The tangent of theta equals the opposite O over the adjacent. So we have so, ka, toa. However, we have recently been in the practice of placing that right triangle on a coordinate axis and labeling the angle still as theta, but noting that this side exists completely in the y direction and this side completely in the x direction, and we have often called the hypotenuse r, because we're going to be thinking about this as the radius of a circle in a little bit. So we're going to call the hypotenuse r. So we can rename our basic trigonometric functions as the sine of theta equals the opposite, y is opposite the angle theta, and the hypotenuse is r. So cosine of theta would be the adjacent side, which is named x, over the hypotenuse, which is r. And then the tangent is the opposite over the adjacent, y over x. Besides the basic trigonometric functions, we also have the reciprocal functions, cosecant, secant, and cotangent. Now, it might be nice if we could keep sine and secant together and call those reciprocals, but that's historically not how they were developed. And so actually secant is the reciprocal of cosine, and we abbreviate it this way. The secant of theta equals the tangent over the adjacent side. Cosecant is abbreviated CSC, so the cosecant of theta is equal to r over y. And cotangent is abbreviated COT. The cotangent of theta is the adjacent over the opposite, which is the reciprocal of tangent. So since those things are true, and we have these pairs of reciprocal functions, we can also write that the sine of theta is exactly equal to 1 over the cosecant of theta, that the cosine of theta is exactly equal to 1 over the secant of theta, and that the tangent of theta is equal to 1 over the cotangent of theta. Now that we have all this information, let's shrink this a bit and let's play with it. Okay? So if we're looking at the sine of theta, what would happen if we just do some algebra with this? What would happen if we divided that by the cosine of theta? Can we analyze what would happen? Well, let's see. The sine of theta we have it up here first in our list, is equal to y over r, and that is divided by the cosine of theta, which is equivalent to x over r. Well, we have a complex fraction here, and to go about starting to evaluate that, we take the fraction that is in the numerator and we multiply it by the reciprocal of the fraction that is in the denominator. And now once we have done that, these r's cancel, and we get y over x. Well, look at that. We already have that defined in our list. So it turns out that sine theta over cosine theta, there's a division there, is equal to the tangent of theta. Now, we usually write this slightly differently. We usually write it as the tangent of theta equals the sine of theta over the cosine of theta. And likewise, the cotangent of theta, which is the reciprocal of the tangent of theta, flips the ratio we had above. So it becomes cotangent of theta equals the cosine of theta divided by the sine of theta. And we can play some more. Remember, we're dealing with a right triangle here, right? So we can use the Pythagorean theorem. We can use the formula to say some things about this triangle. I'm going to go ahead and rewrite it down here. Okay, you will remember that x squared plus y squared equals r squared. Now, as long as we obey the golden rule of algebra and do unto one side as we do unto the other, we can do a lot of things with this. We can divide both sides. We can divide every term in both sides by r squared. Why in the world would we want to do that? Well, something very interesting happens here. We have r squared over r squared, which let's rewrite according to our rules of exponents, x squared over r squared as x over r, that entire thing squared, plus y over r, all of that squared, equals r squared over r squared, just 1. Okay, but x over r, haven't we seen that someplace before? Well, yes, we have. We have seen that x over r right here. And we have seen y over r right here. So we could write that as x over r, the ratio squared, or we could write this as x over r squared. That would be cosine squared of theta. Yes, that's the convention. When you square a trigonometric function, the square goes there, not after the theta. Okay, I'm afraid it's something you'll have to get used to because that's pretty standard. And then we have the sine of theta squared equals 1, which is another identity. So let's put it up here. Cosine squared of theta plus sine squared of theta equals 1. But let's look back at how we arrived at this place. We divided everything on both sides by r squared. Why? Because it was useful. It was kind of fun to see what happens if you do that. Well, as long as we divide everything on both sides by the same value, we can do that with any value. So what would happen if instead of dividing everything by r squared, we divided by x squared? What would we get? Well, we would have 1, because x squared over x squared equals 1. We would have y over x squared, and that would be equal to r over x squared. Now, looking up at our functions above, that means we would have 1 plus y over x. We see that in our list up here as tangent of theta, so we would want tangent squared of theta equals and we find r over x in the next column as the secant of theta. Therefore, down here we need secant squared of theta. And to add this to our list of identities, our new identity is 1 plus the tangent squared of theta equals the secant squared of theta. We've divided by x squared. We have divided by r squared. Let's go back and divide by y squared and see what that gives us. That produces x over y squared plus y squared over y squared is equal to 1. And then we have r over y squared. Finding those ratios in the list above, x over y. We have it here as the cotangent of theta, and r over y is listed as the cosecant of theta. Therefore, we can put those into our formula down here. X over y squared would be the cotangent squared of theta. We add 1 to that, and it becomes equal to the cosecant squared of theta. So we have another identity. So let's make these a little bit smaller here and put them up beside our original trigonometric ratios. And let's make some room at the bottom here, because that's a lot of stuff to remember, isn't it? That all of those are true. Wouldn't it be nice if there were a way to remember this? So, there you have it. Makes it easy, right? Well, maybe if I add a little more detail. In the center here, we put the number 1. And going around this hexagon, we start here with the tangent of theta. We have the sine of theta on top, followed by the cosine of theta. And over here to the right, we have the cotangent of theta. At the bottom, we have the cosecant of theta, and then the secant of theta. If you examine how this hexagon is set up, you can see that a trigonometric function is exactly opposite its reciprocal. So sine of theta equals 1 over the cosecant of theta, or the cosecant of theta equals 1 over the sine of theta. Likewise for the cosine of theta and the secant of theta, the reciprocals are on opposite sides of the hexagon as they are for the tangent of theta and the cotangent of theta. You read across the hexagon to find the reciprocal of a trigonometric ratio. Now be careful with this one. Write it down as you work your way around. We're going to start with the tangent of theta because that's the first identity we have listed up there in orange. The tangent of theta, if you go around in a clockwise direction, you get that it is equal to the sine of theta divided by the cosine of theta. We can continue around the circle to find one that isn't listed. You start at cotangent, going around still in the same direction. You have the cotangent of theta is equal to the cosecant of theta divided by the secant of theta. Perhaps we should check this one. The cosecant of theta is equal to r over y, and that's divided by the secant of theta, which is equal to r over x. That is a division, a complex fraction, so we do r over y times the reciprocal of the denominator. And when we finish up what we're doing there, yes, we're going to be left with x over y, which is the definition of cotangent. We're good. Now the key with this technique is to start somewhere on the hexagon. Identify that starting point, that ratio, and follow it by an equal sign. The next trigonometric ratio goes in the numerator, and the next one you come to in the denominator. And now we have another identity here that we also do not have listed. But is it true? You betcha. I do hope someone out there is asking, what happens if we go in the other direction? Say we start with cotangent, and we come back this way. Will it still work if we go counterclockwise? Well, let's see. Cotangent of theta would equal cosine theta over sine theta, which we already have listed up here. So yes, it works in either direction. One ratio equals the next ratio divided by the third ratio. But wait, there's more. Notice those squares inside those three triangles placed around that hexagon. What could they mean? That's a square. So, and that square is near the sine. So if we were to write sine squared of theta plus the cosine squared of theta, because there's another square right beside that cosine, okay, equals the other point, the other vertex in that triangle is at 1, and 1 squared is 1. Is that one of our identities? Yes, it is. Let's check the tangent. Okay, so now I'm going here, tangent theta 1 and secant of theta. So if I write that out, I would have tangent squared of theta plus 1 squared is 1 equals the secant squared of theta, which is another one of our identities because, look there, it's addition. The order doesn't matter. Let's look at our remaining triangle here. If we take the sum of the values that are on the top, 1 plus, well, 1 squared is 1. And then we have the cotangent squared of theta. Does that sum equal the cosecant squared of theta? Well, yes, it does, because there it is as an identity. These are just in a different order. And it's addition, so we're fine. Please understand that this handy hexagon is just a mnemonic device. It does not prove the identities. The identities are derived or proved from the definitions of the basic and the reciprocal trig ratios. And that's what we have right here. Everything flows from that. This is just to help you remember the relationships, to remember the identities without having to derive them each time. But what I truly want you to be able to work with and to apply are these trigonometric ratios and these identities. So let's do some applications in the next video.